Hello and welcome to a presentation on Sonardyne's latest acoustic inertial position reference systems used for DP. First, let's start by looking at a modern oil field. On the right, the semi-sub is positioned using acoustics and inertial for DP combined with GPS. It'll be supported by other vessels in close proximity using the same sensors and maybe simultaneous operations continuing close by. New vehicle types are starting to appear, such as the wave glider. Wave gliders are persistent, unpowered vehicles maneuvering through the field, collecting data from subsea assets, using acoustics for comms and GPS for positioning. In addition, AUVs that we're already familiar with are starting to be used for intervention tasks, and most vessels these days operate ROVs, both of which position subsea using acoustics. On the monitoring side, increasingly we're being asked to measure pressure, temperature, strain, stresses, inclinations from BOPs, and wider monitoring tasks such as the deformation of the seabed as hydrocarbons are extracted. There are also new sensor types appearing for subsea monitoring, such as the automatic leak detection system. This monitors for hydrocarbons in the water column and reports cases using acoustic data links. So the analogy we can use is the wireless environment that we're used to at home and in the office is now moving offshore and subsea. And whilst this is great for situational awareness, from a DP point of view, we need to make sure these additional tasks are fully integrated and don't interfere with our operations, and that we can free up bandwidth from acoustic positioning to allow for monitoring and communication activities. These challenges are combined with the fact that there's no such thing as a perfect position reference. GPS signals are weak, equivalent to a 40-watt light bulb from a distance of 10,000 miles, and they're also easy to interfere with, a 1-watt jammer being able to destroy commercial GPS for a radius of 100 kilometers. More likely commercially is interference from unintentional jamming due to faulty electronics, poor antenna terminations, and interference from communication systems. Subsea, we've already looked at the challenges of integrating comms and control tasks with our dynamic positioning and making sure they're compatible. Other issues subsea is that although we've put great effort into making acoustic positioning systems reliable with things like LUSBL, availability is still not 100%, and we can have outages in our acoustic positioning due to interference, due to noise in the water and thruster activity. So what we need is a complementary technology that helps us mitigate the risks and challenges with GPS and acoustics. So this presentation looks at the latest positioning systems used for deep water drilling, real-world operation, and how we address some of the challenges discussed, and then the lessons learned. So a Marksman Ranger 2 DPINS system looks like this. In the centre we've got the acoustic transceiver deployed through the gate valve, used to measure vessel position from transponders deployed on the seabed. Co-located with the acoustic transceiver is the inertial navigation system, in this case on top of the pole. Transceiver and INS are connected through the vessel up to the bridge, where there's a navigation sensor hub dealing with all timing and communications, and a PC running either the Marksman or the Ranger 2 software. GPS is shown connected, but this is only required to set the latitude in the gyro and to seed timing. There are also outputs using all the major telegram types to the DP desks. The part of interest here is what's happening with the inertial navigation and the acoustic positioning. So let's start with USBL. USBL, or ultra short baseline, is a basic positioning method that's measuring range, horizontal and vertical angle from a transceiver mounted on a vessel to a seabed transponder. It's been around for more than 20 years, but over time Sonardyne has moved from analog to digital processing, which adds integrity, precision and robustness to both the wideband 2 ranging and the data telemetry. In addition, 6th generation hardware has additional quality metrics that are used for integration with INS. A limitation of all USBL systems is that sound travels through water at approximately 1500 meters per second, so in deep water it can take 3, 4 or maybe 5 seconds to get an update. Inertial navigation has complementary characteristics. So INS is a self-contained sensor. It's measuring Earth's rotation and gravity and using that to compute acceleration, velocity and then change in position. It's very good over the short term and it's very precise, but over the long term it drifts. So it's said to have complementary characteristics to the acoustic positioning system. We can see on the chart here 3 different sensor types. The blue line is our raw INS, the red line is our raw USBL, and the green line is an integrated INS USBL solution. We can see that with time the blue line drifts, so after approximately 5 minutes there's a 14 meter position error. This happens with all inertial navigation systems and is due to the way the errors accumulate in the integration process. However, if we were to zoom in on that blue line, over the short term it's extremely precise and has a very high update rate. In contrast, the red line, which is our USBL position, is as accurate after 5 minutes as it is at the start. However, in the middle there we've got short-term disruption, in this case due to high gain DP manoeuvres putting aeration, noise and thruster wash into the water column and causing position jumps in some cases in excess of 5 meters. What we're trying to achieve is the green line, which is our best of both worlds. So here we're taking the long-term accuracy of the acoustic system and combining it with the short-term precision and high update rate of our INS. And that's what we call an acoustically aided inertial navigation solution. So whilst the principles of acoustically aided inertial navigation are the same across sensor types and manufacture, the implementations are different. The 2 main types of implementation are either loosely or tightly coupled integration. Loosely coupled is shown in yellow on the diagram. Here the acoustic transceiver measures ranges and bearings to the seabed transponders and passes those to the top side for position computation, and it's the USBL position that is then sent to the INS. In contrast, the red lines are the tightly coupled integration. Here the transceiver measures ranges and bearings in the same way, but passes the raw data to the INS for aiding. So tightly coupled has some significant advantages. Ranges we know we can measure quite accurately. We're starting and stopping a clock. Bearings and vertical angles, on the other hand, require measurement of phase across the face of the acoustic transceiver. This has to be done in quite a noisy environment and is sometimes subject to interference. So the bearings get the next amount of weight and the vertical angles get the least amount of weight because of ray bending effects, meaning the angle measured at the transceiver face is often different to the true angle. So being able to weight these raw measurements separately makes for a more accurate and robust solution. The other advantage of tightly coupled is that we don't need a full observation set at each epoch. So at one update we can take a range measurement, the next update we could take a bearing measurement, the next update we could take a vertical angle measurement, and still use those over time to constrain the drift in the INS. So let's take a look at how these systems are used in practice. And it's worth noting that the solutions are scalable from quite small construction and intervention vessels all the way up to high integrity drill ships. So the first application is the Ocean Intervention 2, operating out in the Gulf of Mexico in 3,000 meters of water. Now Sonardyne have fitted single Ranger 2 DPINS systems to all three of the intervention class vessels, and in this case operating in 3,000 meters of water with one transponder at a 4-second update rate. Now these vessels would typically use just GPS for DP. Deploying a full LUSBL array can be quite costly and time consuming considering the nature of the work they do. So installing the DPINS system has allowed them to improve vessel utilization and DP reliability, which in turn reduces downtime. So the system installed on the OI2 looks something like this. We've got an acoustic transceiver deployed through a gate valve with a Lodestar INS mounted on top of the pole, one seabed transponder in use for DP, second one deployed as a wet spare. Now the transceiver and the INS are both powered and communicated with separately, which means should the INS fail, we can fall back to using the vessel's gyros and VRUs. Data is passed up through the ship's cabling to the bridge, where all I/O and timing is dealt with in the NSH, and then the position is computed on a PC running either Ranger or Marksman software. So this diagram shows the performance of the system. Operating in 3,000 meters of water, we're achieving approximately a 2 meter accuracy, which is equivalent to 0.08% of water depth. With the USBL system alone, this data would be much too noisy for use as a DP reference, and we can see here over time that our position accuracy is consistent and stable at around the 2 meter mark. So in addition to the accuracy achieved, we can now bridge through acoustic outages using the INS, and we can provide a fast update rate into the DP disk, somewhere between 1 and 5 Hertz to match the GPS, rather than it being 4 or 5 seconds, which is what we would have with acoustics in 3,000 meters of water. So moving on from a lightweight construction intervention vessel to a semi-sub doing workover activity again in the Gulf of Mexico. Class of this vessel was DP3, so we need a dual system. In this case it was a dual independent LUSBL system, and one half of that was upgraded to tightly coupled DPINS. Another advantage of the INS system is it allows us to reduce the update rate to the acoustic transponders, and in this case it was reduced from what would normally be 3 or 4 seconds down to 15 seconds, which extends the battery life of those transponders. And the acoustic system on this vessel was a 5th generation. It's also compatible with INS, but it's 1 generation old. So this is what the system looked like. On the left hand side is our DPINS system. We can tell this because we've got a Lodestar mounted on top of the pole and fewer seabed references, in this case 3. On the right hand side is our traditional LUSBL system with no INS and 5 seabed transponders. Yellow hardware means it's the 5th generation system, and the benefits were the same. We're now operating independent from GNSS. We've got a 1 to 5 Hz update rate going into the DP desk. We can bridge through the acoustic outages, and we've got fewer seabed transponders on our DPINS system. The other advantage of this setup is diversity of technology. So we've got two fundamentally different positioning methods on each side of our dual independent system, which means there's no software single points of failure. This is the performance of the INS system installed on one of the poles. So in 1,000 meters of water, we can see that with two transponders, our position accuracy is about 0.5 of a meter, and that's over an extended period of time. And we're looking at the green line, which is our INS 1D RMS figure. When we move to 3 transponders, the accuracy is now down at 0.2 of a meter, which is approaching GNSS levels of performance with 3 seabed transponders. When we look at the DP desk, we can see here that we've got 3 GPS inputs, GPS 1, GPS 2, GPS 3. Our INS solution is HPR 1, and our LUSBL solution is HPR 2. The first GPS was artificially de-weighted by the DP operators because they had lost confidence in it, but we can see with the other references they're all achieving an equal weighting in the DP desk, which makes for a very reliable and robust DP solution. Then when we simulate a GNSS outage, we can continue to operate on 2 independent and different PME types, so the DPINS solution and the LUSBL solution, in the absence of GNSS, and the vessel held station on DP whilst we did various heading changes and box maneuvers. So now we move on in scale again to a drill ship. This is Vantage's Tungsten Explorer. Came out of the shipyard in September 2013 and is now operating in Myanmar in about 1,000 meters of water. So this is a state-of-the-art acoustic inertial position reference, world class because it's got 2 acoustic inertial systems, 1 on each pole. Again, they can extend transponder battery life by reducing update rate, and it's fitted with 2 of the latest 6th generation wideband transceivers and is using 6 seabed transponders, 3 per system. So this is what their system looks like. INS is installed on both poles and 3 seabed transponders associated with each system. So again, they're getting the fast update rates into the DP, they're bridging through acoustic outages, they're potentially saving on seabed transponders compared to a traditional LUSBL, which would have 5 on each side. And both of these systems will gracefully fall back to LUSBL should there be an issue with the inertial navigation. Performance we're achieving here is very similar to what we had on the semi-sub. With 3 transponders, we're getting GNSS levels of performance independent of water depth, and when you zoom in, you can see that the track of the inertial solution follows very closely with the GNSS. So our Marksman and Ranger 2 DPINS systems have been installed on many vessels now worldwide. This next section is just a short look at some of the lessons we've learned. So first of all, for drill ships, workover vessels, or vessels involved in diving operations, we should not be using a single seabed transponder for our DPINS solution. And this slide shows why. On a vessel operating out in the Gulf of Mexico in 2,800 meters of water, we can see that over time our USBL position goes from quite stable to quite noisy for an extended period of time. So that noisy USBL data found its way through into our INS solution, and the green line in the bottom chart shows our INS error increasing and becoming unstable. That resulted in the DPINS solution being rejected from the desk. So the sudden and then long-term degradation in USBL was because of a changing heading and the fact that the transponder was obscured from view of the transceiver due to the riser in the water column. So to overcome this, we need to be operating with 3 or more transponders when we're doing drilling, diver operations or workover operations. The next lesson learned is the fact that we need to use a tightly coupled integration of our acoustics and INS. The two charts show the same data processed twice with the same vertical scale. So the loosely coupled solution has an accuracy of around 5 or 6 meters. This is using 2 transponders and is a poorly configured system. When we move to the tightly coupled solution, the accuracy is improved to about 2 meters using exactly the same data. So tightly coupled is more accurate and is more likely to be accepted in the DP desk, and in fact this loosely coupled data is not suitable for DP. Another thing we get asked about a lot is how many transponders should we use in our DPINS solution. And this slide gives some indication of an example in the Gulf of Mexico operating in 2,800 meters of water. So we can see on the graph number of transponders against position error, and with 1 transponder our position error is about 2.3 meters, with 2 it's 0.6, with 3 it's 0.2, with 4 it's 0.18. So we can see a law of diminishing returns there, and the optimum number is between 3 and 4. Then when we look at INS installation, we've learnt that we need to co-locate our acoustic transceiver and inertial navigation system. This is a test done on a vessel with stem tubes where we've got an INS co-located with the acoustic transceiver in a configuration we call gyro USBL, and a second INS installed on the bridge. Now the DPOs did a test by pointing the thrusters at the pole at about 70% power to see how much the pole would move, and we could see in the charts that in roll the pole starts to resonate. So this resonating motion is sensed by the INS on the pole, it's not sensed by the INS on the bridge. In actual fact, resonating about the true value is not too much of a problem. The INS can smooth that out quite well, but in pitch we can see that we've got a significant bias as the pole is pushed aft. Now that bias is measured by the INS on the pole, it's not measured by the INS on the bridge. So if we were dependent on an INS installed on a bridge or in a gyro room, we'd see a 0.3 degree error in pitch, which in 3,000 meters of water relates to a 15 meter position error. So that's unlikely to be usable for DP purposes. So the lesson learned is we must co-locate our inertial navigation system with our acoustic transceiver. If the pole is rigid, the lodestar can go on top of the pole. If it's a stem tube, over the side pole, or there's doubt about the rigidity, then we need to mount the INS with the acoustic transceiver on the bottom of the pole in a configuration that we call gyro USBL. This is what that test looked like in the DP desk. We can see we're tracking using our INS solution. The thrusters were pointed aft towards the pole, and we continue to navigate and hold station during that test, and that's thanks to the instrument on the right, which is our gyro USBL. So we've gone through a lot of data, a lot of detail in time series plots, which can be quite complicated to understand, but fundamentally there are two things to remember. If we want accurate, high integrity acoustic inertial navigation, we need to co-locate our INS with our acoustic transceiver, considering using a gyro USBL, and B, we need a tightly coupled integration so we can take those ranges and bearings, weight them differently. Thank you for watching. Please email any questions to sales@sonardyne.com and subscribe to the Sonardyne YouTube channel for more information.